Okay. All right. Can everyone hear me? Can everyone see me? Are we back? All right, fantastic. I hope you enjoyed that clip. Konami, they're not much of a game studio or publisher anymore these days, but they certainly gave us a lot of laughs when they were, and a lot of great games too. Okay, so let's go ahead and get started here. We've got some space ambiance in the background. Hopefully that gets us into the thinking mood here. Okay, so SIMD, right? Single instruction, multiple data. What we're going to discover is that it's kind of a different paradigm. It's a different kind of approach to programming that is going to feel a bit uncomfortable at first, but that is the way that shaders are programmed. That is the way that we can get really, really cool, diverse effects, like what we see in this kind of image right here. Has anyone played Mario Odyssey? Has anyone played Mario Odyssey? So this is a boss from that game, and this boss has a really cool intro. The development team needed a way to make this boss feel extremely powerful, and the way that they decided to do that was by taking your screen and saying, when the boss hits and slams the ground, boom! Not only are we going to have screen shake, and we're going to have stuff falling from the ceiling, we're also going to have the screen itself. We're going to take the pixels and we're actually going to blur them, okay? If you look for just a second, boom, right there. The screen pixels, they're kind of blurred based on how far away they are from the center of the screen here. You can see that pixels at the center of the screen are much less affected than those on the far side of it. Boom, right? As a result of this impact blur, you feel like this hit was really, really powerful. It changed your ability to see. And so we get this really, really nice emotional impact there. Okay. Come on, let's progress. I'm clicking here. Google. I hope my account doesn't get banned for saying this, but I have to say the reliability of Google products lately it's been a little bit sus. So hopefully they get their act together. Okay, so shaders, right? They can be extremely powerful, and not only for giving people the feeling of impact, but it can also be used to produce other feelings. For instance, the feeling of heat. Okay, this heat distortion that we see in this right GIF is the exact same visual effect that humans see when they look at a distance over a very, very hot environment. For instance, if you think back to high school and looking over a blacktop, right, a parking lot maybe, you would see this kind of distortion in the distance. And so recreating this in a game gives us a similar effect. You can use shaders and SIMD programming not only for cool emotional effects, but also really cool scene transitions. This one over on the left is something that you can actually download from the course repository. When you click a button, it actually brings in this shape, goes to black, and then brings a new shape out, and then goes fully to scene, okay? Another thing that's kind of interesting to notice is whenever you click here, when we click the button, the visual actually kind of morphs down there, as if we are clicking into a pool of water. And that's kind of a neat effect. You can look at it closer. Come on, click. There you go. Boom. It's kind of subtle, but it is very cool. Another way that you can use these kinds of techniques is for actual gameplay purposes. So this is a firefighting game that we had been working on for quite a while. It's still, it's in development. This project isn't finished. It was mostly a prototype project. But shaders can help you go from an effect that looks like this. A bunch of balls water represented by a bunch of balls, a bunch of teal spheres, to something that's much more convincing, this beautiful kind of 2D effect with outline and all. Let me see if I can find more stuff here. This is a presentation I did at the local IGDA. Pixel Junk Shooter has a very similar technique that they use. Essentially, what we're doing is we have these particles in our environment that are spheres physically, and they can flow as a result. If you shade them in a really interesting way, however, you can actually turn them into a 2D, seemingly kind of connected volume. Instead of all these discrete spheres, you get this really organic kind of body that forms. And as you improve it, you can actually make it look a little bit more convincing. You can make it flow a little bit better down hills, make it a little bit less goopy and rigid and more like the water we expect. Eventually, we were able to get the effect to be like this. Oh, come on. We'll go ahead and zoom in for you. Okay, so we're running around. We've got water you can spray out. You can send it up slopes, and it will physically react as you'd expect. It will come flowing back, which is really, really cool. And all of this, essentially all of this, it's sort of like a ball pit, right? What you're really doing is you're spraying and spawning a bunch of water spheres at once. However, the only thing that changes is the way we render those spheres. Instead of showing the actual sphere mesh, what we do is we draw these spheres onto a texture, a render texture, and we process that render texture a bit, we threshold it a bit to get this kind of cool shape. And as a result, yeah, it looks pretty nice. You can influence it by running around, by jumping. You can make splashes inside of it. It wasn't very performant, but it did work pretty darn well. So, anyway, okay. And that's just the power of shaders. Another really cool thing, this one using a stencil shader, was you can do smoke, which can look pretty cool. Yeah. Anyway. Come on, let's go. Okay, so we've got some smoke over there. This is a weird game. You started off as like paintings. Anyway, okay. So let's go ahead and get out of that. Shaders can be extremely powerful, in particular because they are something that are hard to create. They are very difficult to program. They tend to give you effects that will take your game very quickly from looking like a student game, like a hobbyist game, to looking like something that was done by a professional, simply because many, many games lack these kind of effects. Or if they do have them, then they are from a standard asset pack, so they're the same shaders, the same effects you see in every other indie game. Okay? Now, a bit of a warning. I've said it a few times, but this is a really new way of programming that you might not be used to. And so you've got to hang in there. You've got to be ready to kind of put forth an initial investment, go through a little bit of pain to get to a point where you can really wield these powerful techniques effectively. I really like this comic. It is an author, I believe a comic artist, who's asked, how do you draw so well? She says practice. Then the person who's asking says, it must be an innate gift, a gift from God. No, it's practice. And then someone who says, I'll never understand how some people are so talented. It is a mystery. No, in fact, it is practice. And in many ways, a little bit of pain and a lot of boring nights until you get to the point where you can really do cool stuff. Okay? You already know that, though. Okay, so I have a challenge for you, chat. I have a challenge for you. And we'll see how you do, okay? Your challenge is to get your deck painted, all right? Now, I'm not sure how many of you currently have a deck, but at some point you probably will, sometime in your life. And so the question is, how are you going to get your deck painted in the most efficient way possible? So here are your options, chat, and I'd like to hear your thoughts on them. Which one's going to be better? 2 options. First of all, you have Captain Painter Ultimate. You look in the yellow books, you do a map search, and you find out there are 2 services locally. You've got Captain Painter Ultimate. This is essentially a painting super soldier, the best painter in town. This person has incredible equipment and is able to paint really fast. This person can paint anything you want. It doesn't matter if it's your deck, or if it's your ceiling, or if it's the super intricate artistic structure. This person, Captain Painter Ultimate, can paint it for you, okay? Next, your other option is the group painting unit, okay? This is not one person, but this is actually a traveling team of painting soldiers, okay? They have their paintbrushes at the ready, and while they're not super fast, there are a lot of them, okay? So they can work together pretty well to paint stuff. However, they can never split up. They can never separate from one another, and that's really important, okay? So the question is, do you want one super soldier to paint your deck, or do you want 1,280 soldiers to paint your deck? All right? Who are you going to choose? Who gets it done faster? And let's go ahead and take a vote, chat. Okay, who's totally going with the Captain Painter Ultimate? Who wants Captain Painter Ultimate, and who wants the group painting unit? And just for abbreviation, to make these names a little bit easier for us, Captain Painter Ultimate could be known as your CPU, which stands for Captain Painter Ultimate. And the group painting unit could be described as a GPU, which stands for Group Painting Unit, okay? That's all it stands for. Okay, so team, do we want the CPU or the GPU painting our deck here? You have a small deck. You'd like to pick the CPU. Okay, that makes sense, actually. We've got people saying the CPU. We've got people saying GPU. We've got a lot of people saying the GPU. Okay. Okay, so I have another question for you. I'll reveal the answer later. I have another question for you. You have a challenge. You are lost in a maze. You go to, it's the fall, let's say, in Ann Arbor, and you go to a corn maze, okay? And you get lost in the middle of all that corn, okay? Now you've got a phone, so you know you got to call someone. The question is, are you going to call the Captain Painter Ultimate, or are you going to call the group painting unit to come through this maze and find you? Now, here's the thing you have to remember, okay? Here's the thing you have to remember. The CPU is very fast and very self-sufficient, okay? Captain Painter Ultimate can do anything, really. Can explore and make decisions really quickly, can move fast as an individual. Now, the group painting unit, while there are a lot of people in this unit, they move slowly, okay? They move slowly, and they can only move in lockstep, which means they always have to travel together, and they always have to do roughly the same thing as everyone else in their platoon, okay? So the question is, who are you going to call to get to you and find you faster in this maze? Jelly Kid Forever says the Chief, because it is the Chief, okay? So here's the thing, the GPU could probably search through this maze to find you eventually, but its numbers really aren't going to help it at all. It's very slow, and it's not like they can split up. The GPU cannot split up its various soldiers to tackle and explore all of these different places in parallel. It can't really do it. If one soldier goes one direction, they all have to go that direction. Okay, so let's go ahead and cast this overdone joke aside. I'm really talking here about the CPU versus the GPU. Okay, instead of talking about soldiers, I'm talking about cores. Okay, with the CPU, this tiny but extremely powerful chip, you have one or, usually single-digit cores. Sometimes you get up to 8, sometimes 16 maybe. But these cores are extremely fast, extremely flexible, very self-sufficient, and they can all do different stuff. They can all do different things. They can tackle different diverse operations while their other cores are doing different things, all right? Now, the GPU is really interesting because it has cores too, and it has way more of them, all right? So compare one core to 1,280 cores in my GeForce GTX 1060 that I have here at home. Now, this CPU might have one core versus 1,280, but you have to understand that these cores are not made alike. These 1,000+ cores over here, they're extremely cheap, They're very, very cheap, and they're very limited in what they can actually do. They all have to move together. They can't go and do separate things, okay? These cores all need to roughly be doing the same exact operation as all their other cores. And that's why we can have so many in one device. This device, 1060, I think it's less expensive than a high-quality Intel i7 processor, despite having way more cores. That's because the cores that you jam into this machine, they're all extremely basic and very limited, okay? But there's so many of them that sometimes you can do some really powerful stuff. So the example of painting your deck, right, that's essentially analogous to painting your screen, all right? So that is where the GPU is going to be really, really powerful, and not so much the CPU. CPUs versus GPUs is a really, really powerful idea these days, and an interesting conversation. Back in the 60s, right, as processors were first kind of being built and improved, Moore's Law came about. And essentially it said that transistor count would double every 2 years or so. As these companies found new ways to make their transistors smaller and smaller and smaller, they started getting much more performance essentially for free. However, this performance didn't really last, okay? As time went by, the transistor count kind of continued to rise, but the single-threaded performance of these processors started to kind of taper off. That's not good, okay? Consumers won't keep buying processors if you can't find a way to make them better. And so if we're not going to get single processor performance to improve as quickly, then we need to find another way to improve these processors and let them do more. And the way that they started to do this was by not increasing the single core performance, but increasing the number of cores that you have, right? The number of independent, flexible cores so that you can maybe not move faster on a single operation, but do more operations in parallel. So that gets you additional performance that way. Okay? So anyway, when you think about CPUs, right, they have incredible single-threaded performance. They are incredibly flexible and powerful, but they are still limited, okay? They're really good at things like pathfinding, where you need to do some pretty intricate decision-making, and you need to be very flexible in how you kind of traverse and explore this area. However, if you think about an operation like painting a deck or painting your screen, you don't really need quite as much decision-making, right? All you really need are a bunch of dumb cores that will just simply stand there and then paint the pixel they are given, okay? And so having a ton of cores in this situation makes it way, way better fit for a GPU than a CPU. Okay. So I have a third challenge for you. You need to paint your screen during gameplay, and your game must paint the screen 60 times per second. Now that doesn't give you a whole lot of time to actually do this, okay? 16 milliseconds is roughly all the time you're going to have to paint the entire screen. So what happens if you ask your CPU to do this? If you ask your CPU to paint every single pixel of your screen, it will have to do something sort of like this. It will have to iterate through every single pixel. Okay, so it'll iterate through the X values, 1920. On a standard screen, you'll have 1920 by 1080. And then it will have to iterate through the rows of your screen. It'll have to iterate through the columns. And essentially, you're going to do around 2 million paint operations on this one CPU, okay? You have to look up what the current texture you need to render is, and you need to go ahead and render that pixel. And that's really not great. That's going to take about 2 million operations, and you might have a super fast CPU, but that's still a lot of operations to have it do, okay? Every single frame, oof. That's nasty. If you do it this way, I believe it's usually referred to as software rendering. You're asking your CPU to go from pixel to pixel and grind out those simple calculations one after another. and it doesn't usually go very fast. Compare what the CPU does up here to what the GPU does down here, okay? Whereas the CPU needs to have these 2 for loops that allow us to iterate through every pixel, the GPU simply has 2 lines of code. Just, hey, you are given, every single core on the GPU is given its own pixel. And, you know, it's given an X value, right? Say, what pixel are we rendering today? A Y value, what Y coordinate of the pixel are we rendering today? It uses those 2 pieces of data to look up what the color of the pixel should be, and then it simply paints that pixel. What's amazing here, and very strange, is that this function right here is what the GPU cores run. The CPU cores run this function. As a result, the GPU, each core, doesn't have to look at any other pixel. It only looks at the 1 or sometimes handful of pixels that it is given. And so it doesn't have to go through those for loops. It knocks out a ton of complexity right there, and it moves way faster. Instead of 2 million calls, paint operations, that the CPU does, essentially 2 million operations are done completely in parallel on the GPU. Or in other words, the effective amount of operations that the GPU did was 1. Okay, so we've gone from 2 million to 1. Now that 1 operation is executed a bit slower than what the CPU could do, but because it's only 1 operation, it blows the CPU out of the water, okay? So how many paint operations occur? Up here, we have around 2 million paint operations. Down here, with the GPU, we have 1 paint operation. And this is where that term I said a few times comes in, SIMD. With the GPU, we have single instruction, multiple data, okay? You have a single block of code that all of your cores run, but the data that comes into that block of code is different. Single logic, multiple data. Single instructions, multiple data that those instructions execute, okay? In a different sense, SISD, single instruction, single data. This GPU has a single block of logic, and it also has a single block of data, and it has to iterate through all of it, okay? It's a huge block of data, it has to iterate through all of it and do the job, and it's just slow, all right? So anyway, that is where SIMD, that phrase, comes from. You have a bunch of different diverse data, all the different pixels, but you only have a single instruction that's going to receive all of these. Okay. So anyway, here's I don't really like this example too much, but the logic that a GPU can run can be more complicated than simply take the pixel that you're given and render it to the screen. It could be a little bit fancier, right? It could not only be given the coordinates of a pixel, but it could also be given a texture, right? And maybe that texture determines, you know, whether that pixel is supposed to be black or whether that pixel is supposed to render the actual final scene. So this is the pseudocode that the GPU runs when we render this transition image. It looks up what the original texture would have been if this kind of black outline wasn't there, this shape, this cutout shape wasn't there. It then determines whether or not it is inside this shape and then checks whether it should use this shape and show the actual final scene or whether it's outside of the shape and it should show a black pixel instead. Okay? So there can be some logic that each of these really cheap GPU cores considers when it goes to render that pixel or not render it. But generally, if your logic gets too complicated, you'll find that your shader code just falls off a cliff in terms of performance. So you need to be very careful. GPU cores are not the same as CPU cores. All right, let's keep going. One of the really cool things about shaders in working with the GPU is that you don't only have to give it pixels like we did down here. You can actually use GPUs and their unique kind of SIMD method of processing to rapidly and efficiently transform other pieces of data. Not just pixels, but vertices. So vertices, right, they are all of the points that make up a mesh. And if you have let's say you have a rectangle. Let's say, sorry, not a rectangle, a rectangular prism. You have this big rectangular prism, and it's kind of flat, right? If you put a blue texture on it, it might look vaguely like water. But if you want to give it that nice flow that water has, then you need each vertex, each little point on that mesh, to go up or down based on where it is. Where it is in the mesh, and what time it is, right? So you can get that flow, those waves that happen over time. And so that is called a vertex shader. It doesn't transform pixels and paint them to the screen. It transforms vertices on models in meshes. You could have geometry shaders that can actually generate new geometry over time. So this begins as a cool little sphere mesh, but then new vertices are generated to give it this really crazy visual effect. This is the kind of thing that you don't expect to see in just about any student games. So if you want to make your game look really special, you might consider exploring things like vertex shaders and geometry shaders. Okay, and there's actually there's links to the public repositories where you can examine and study some of these things on your own if you want to. Okay. There's a series out there that's really cool. It's called Making Stuff Look Good in Unity, and I guess we'll look at it really quickly. It's a series that is dedicated to how can you implement the kind of AAA graphical effects that we see in games inside of Unity, right? In a pretty hobbyist-friendly way. So how can you get the really cool explosion effects from Legend of Zelda: The Wind Waker? How can you get effects like scanning the environment in No Man's Sky? Let's keep going here. I think I have an example here. Yes. So how can you get the really super cool scanning effect where you see this color distortion kind of spread in a ring throughout the environment? How can you create things like the Pokemon battle intro effect, where the screen flashes down, 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 bump, 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 right? How do you get the really cool screen distortions that get you really excited to go into an intense battle? There are other there are other ways of programming shaders and other tools out there. This is an example of a shader graph that try and make it a little bit more user-friendly to create shaders. However, today I want to take you a little bit low level and show you how you can write raw shader code to get some of these effects. And then maybe in the future we'll come back to and show you shader graph, okay? So today, with the final 20 minutes that we have, we're going to create a very simple underwater effect that looks roughly like this, okay? Where you've got a background and it's got this really cool whoosh that is kind of happening. Now, the general approach that we're going to take to this, by the way, you can go ahead and download this Unity package if you want to. The way that we're going to approach this is we're going to take a final rendered image of our scene, right? The normal thing that the player would ordinarily see, just a few shapes and a blue background. Now, we actually have the ability to take the final image that's about to be shown to our player and we can intercept it. We're going to intercept this image and we're going to tell its pixels to essentially shift over a little bit based on what time it is and where that pixel is on the vertical axis. Essentially, we're telling the pixels to say, hey, instead of rendering the pixel you were going to render something that is shifted off a little bit on the x-axis. In other words, the colloquial way to think about this is if we could tell a pixel, hey, dear pixel, what if instead of drawing where you were supposed to be drawn on the screen, we draw you slightly ajar from that location, okay? There are a few things that we can use to do this. We can intercept the final camera image via a material, via a shader on that material, and the onRenderImage function. Okay, it's going to look roughly like this. There's a special function you can put into your components called onRenderImage. It takes in a render texture, and it is also given a destination render texture. We can write from the source to the destination using a material to change what that source looks like, and then get it out to the screen, okay? So let's go ahead and open up Unity and get that done. Come on here. Hopefully it doesn't take too long. Does anyone, we kind of skipped questions at the halfway point here. Does anyone have any questions about any topics today? Efficient teams, presenting, SIMD shader programming? Again, the main idea behind SIMD and programming shaders is that you go from programming in terms of one super flexible CPU to programming for many CPU cores at once. In other words, GPU cores. They all have to do the same thing, but they are given different inputs. Okay, so here's essentially what we're going to have. We have this scene set up right here, and it's going to look pretty cool. Right? Let's go ahead and create a new scene really quickly. We'll have to move a little bit fast. Let's create an empty scene, boom, just like that. We're going to need a camera, first of all. We are going to need to change the background a little bit. We want a solid color. Let's go for this nice kind of light blue. It looks a little bit underwater-ish. Let's take this camera to our origin, back it up a little bit. We're going to create some objects now. We're going to create a cube. Take it to the origin. We're going to create a sphere. What do we got here? Yep, there we go. Take it to the origin. We'll move it. We'll just keep it there. That's fine. And then we'll create a capsule or cylinder. That's fine. Bring it to the origin. I wish Unity would just put objects at the origin sometimes. That wouldn't work in all scenarios though, so they shouldn't do it. Okay, so let's see what view we got here. We'll move the camera a little bit closer, and here's the view that we have. We'll go ahead and grab some materials here. We've got some coloring materials. We've got the reds, we've got greens, we've got purples. Doop, doop, doop. It's really dark in here. It's because we don't have a light, so we'll go ahead and grab a directional light. That looks a little bit better. Yeah, that looks fine. Okay, so now what we want to do is we want to save our scene, of course. Demo 2. No, not demo. That should be demo 1. That's okay. All right, so let's go ahead and play our game. We can see now that, okay, nothing is really changing. We're just getting the final image that you might be used to. We're not doing any image effects or anything to this. And so we need to start applying a material to our camera. We want to take our camera, we want to take the final rendered image from that camera, and we want to mess with it, okay? So let's call this underwater screen effect, screen effect 2, okay? So we have this new component. It's sitting on our camera. Because it's sitting on our camera, it can intercept that final image that the camera is about to show the user. We're going to intercept that image, and we're going to mess with it a little bit. The way that we mess with it is through a shader, but we need a material to actually do it with the shader. So it's a little bit confusing. I'll explain it again when we get to that point. But, come on, Visual Studio, open up. We're running out of time. Got 12 minutes here. I think we can still do it. Okay. So, the first thing we're going to need is a material. Let's call this a water material. We'll make it public so that we can drag it in. We're going to need to start using the function we talked about, onRenderImage. In order to, so essentially we're given, source is a parameter that comes in, and that is the final image. That is the final texture that's about to be shown to the user. We also have a parameter, the destination render texture. This is the texture that the user is going to see, okay? And so we want to put the source texture data into the destination texture data, and we want to do that by altering it a little bit. We're going to go graphics.blit. We want to copy the source texture into the destination texture, but we want to do so while making a couple changes. We're going to use this water material as a way to intercept that data and change it. So water material will be given the source. It'll be given the source texture, and whatever changes it makes to it, that will be put into the destination texture, okay? So now we actually need to create a water material and then drag it into that location. So let's go ahead and create a new material. A new material here. Create, let's see here, new material. We'll call this water material 2. Now, if you look at this material, you can actually customize it. A material, I'll remind you, is a combination of a shader, the logic that kind of controls how something is rendered, with the assets that that logic needs. So if we look on the standard shader, there are a ton of assets we can send in. We can send in color maps, we can send in metallic data, normal data. However, there are many different shaders we can choose from. Unfortunately, none of the shaders in here are going to give us that cool water effect. Well, we already have one of them, water screen effect shader, but we're going to create a new one, okay? Let's go ahead and create a new shader. We're going to go into create, shader, and then we want an image effect shader. This is a pretty simple shader template that's going to let us take our screen data and manipulate it in a pretty simple way. We'll call this water shader 2, okay? We can double click this, and we're going to, when we do so, Visual Studio is going to open up. Okay, so this is shader code. And it's going to look a little bit funky to you, probably. It's actually, it is a language called CG. It was created by NVIDIA, and it is kind of based on C. So let's go ahead and first come up here, and we're going to change the name of our shader. We're going to call this 494 Water Shader 2. So we'll be able to find it in our little shader menu at this path. So that should work all right for us. So let's go ahead and go in. There's a ton of weird code in here. Structures with interesting data. If you ever look at a structure, you'll see a data type, a float 2. So a pair of floats. A float 4, 4 floats. And what is that called? A 4 tuple, I think, of floats. You'll also see this unique kind of semicolon and then label syntax. This, I don't think this is actually in C. This is unique to CG. Essentially, this takes a variable and it tells the CG compiler what that variable is used for. So this UV variable is given the label texture coordinate 0, as in this UV variable is going to be the XY UV location of where our pixel actually is on the screen, okay? So this weird syntax simply tells the compiler what variable is supposed to be what. What does it represent? Okay, so the function that we actually care most about is in here. It's called frag, the frag function. This is the function that receives the pixel data and is responsible for kind of altering it, and whatever color it returns from this function is going to be the color that this particular pixel gets. You can think of this I variable that comes in, this input, as being a pixel, some pixel data, okay? This I comes with UV values, and you can use it to look up the normal texture at that location. So currently, we're given this kind of template function here. Its only purpose is to look up the color that's supposed to be at our current pixel's location, right? So look up the color in the main texture we're given, as in this main texture is the texture that would normally be rendered to the screen. So grab the color data out of this texture here from our pixel's location, and then simply take that data, which is put in a fixed 4, so essentially a 4 tuple of numbers, change the RGB data into the opposite of what it actually is, and you get an inversion of the color of the screen. So let's go ahead and make sure this is the case. We're going to take our water material, we're going to find our new shader, there it is, Water Shader 2, and then we're going to tell our camera, our Underwater Screen Effect 2 component, that the material that it should be using to convert the source image to the destination image is the water material, which is our water material 2, okay? When we play this, we should expect the colors here to invert. Hey, there we go, there we go. One of the coolest things about programming shaders in Unity is that you can actually work on them while the game is running, and you can instantly see the change. So let's go to, where is it, Water Shader 2. Let's say we want to get rid of this inversion right here. So now we're not inverting anything. We're simply looking up what color our pixel should be, and then we're returning that color for our pixel. And we're back to normal. There we go, okay? So what we want to do here is we don't want to grab the exact location of our pixel. We want to actually grab a location that's slightly messed up. So let's go ahead and create a new variable. Let's call this UV custom UV, okay? And first of all, we'll just make this the default UV, and we'll just put this in and we'll make sure it doesn't break anything. Okay, we'll come back here. Nope, looks good, okay? Now, what we might want to do is we might want to change it in some way. Let's say, you know, we want to have our X and Y values be different. We will have our Y values be the same, I.UV, which is a 2-tuple, .Y. Let's go ahead and say, oh, I don't know, 0.5. I have no idea what's going to happen here. Whoa! Okay. So essentially what's happening is every single UV is only rendering what it finds in the center of the screen. So let's go ahead and change this a little bit. Let's go I.UV.X. This is the normal X location where we would normally render the pixels, so our screen should fix itself. But now what we want to do is we're going to add 0.25. We're going to add 25%. So we should see everything shift over. Bingo. And that's what happened. By the way, UV, these UV coordinates go from 0 to 1. So it is a little bit different. 1 means you are on the far right side of your image. 0 means you're on the far left side. 0.5 means you're right in the middle. So what we'd like to do is we'd like to have this shift over time. So let's say 0.1, we want to shift ourselves on the x-axis by 0.1, but we actually want to do this. Over time. We can actually use a function to do this. It is the sine of time function. So we're going to go ahead and grab that really quickly. So sine, we're going to take the sine value of time, and let's go ahead and get rid of that. So as time goes on, and this syntax is going to be really confusing to you. Essentially, _time.z means you want time, a value of time that's progressing forward, but it's going very fast. If you provide x or y instead, you'll get values that go progressively slower. I have no idea why they chose to do it this way. It's very confusing, but you eventually get used to it. Just think of this value right here as a value that increases with time and does so pretty quickly, okay? Let's see what happens. We should expect to see our x value, where we render our pixels on the x-axis, going back and forth over time. Let's see if that's actually what we see. There we go, we got it. But here's the thing. We want it to whoosh, right, and get this beautiful underwater effect. In other words, we want your position on the sine curve, the sine wave, to be a function of where you are on the y-axis, okay? So, inside of the sine function, we actually want to change your position based on your y value, okay? So actually, let's go ahead and just put that in there. Woo, that's pretty cool, isn't it? That's pretty neat. If we multiply this value by 5, let's say, we can kind of distribute your values further and less cohesively along the sine wave. So hopefully we'll see this get more squiggly. Oh yeah. Now, whenever you get a parameter like this, you always have to push it to 100 so you can see what cool effects you can get. So instead of 5, we'll do 500. Whoa! Look at that. It looks like a signal flying through the air. We're no longer underwater. We are this kind of beautiful signal. Wow, that's really, really cool. It's disco, absolutely. So anyway, let's go ahead and be a little bit more sensible maybe. We're gonna reduce our frequency of our wave, and we're also going to shrink the amplitude of it. Oh, that's pretty intense still, but I do kind of like it. Let's go ahead and move this to 2, reduce it even more, and let's go ahead and reduce the frequency as well. Oh, that's super beautiful, isn't it? That looks really good. Anyway, so this is an example of how you can kind of adjust your pixels. You can get control of pixels, and you can use logic to decide not only what color you want them to be. If you want them if you want to invert them, for instance, when you take damage, you invert the pixels on your screen to give you kind of a shocking effect to your user. But you can also control where they are. You can control what they do. It's even possible, and we might go over this next time, it's even possible to send variables into this shader from your C# code, and that can allow you to do even more interesting logic. For instance, if you have the user click someplace, you could send the click inside of your shader, and you could adjust your pixels on the screen based on where that click actually happened on the screen. That's how you can get cool wavy effects whenever your user clicks, as if your screen itself is made of water. So stuff like that. Anyway, yeah, we ran out of time a little bit. I would have shown you a little bit more, but you can do a lot of really powerful stuff if you don't get too intimidated by the SIMD code that you're writing. Okay, it's a little bit of a different mental model that you need to have when you're dealing with shaders. Remember, SIMD, single instruction, multiple data. You are writing one block of logic right here that will then be executed by many different cores at the same time with slightly different inputs. Okay, the logic is the same across all of your GPU cores, as in all of your pixels, but the data that comes in, the pixel that GPU is assigned, that core is assigned, is slightly different. Okay? Anyway, so that's essentially all I want to get to today. I'll stick around for about 2 or 3 more minutes, and you can ask any questions you want, and then we might return to this a little bit later because it is a very interesting topic, okay? And it's becoming more important all the time. All right, so go ahead and ask any questions you want. We'll pump up this wonderful space ambient music. Hopefully we don't get DCMA'd as a result. Yeah, I wish you the best of luck with your deliverable on Monday. Monday will not be another normal lecture. It will be a playtest session. You'll be given about 2 hours. In reality, you can take that lecture time, but you'll actually be given more. You'll have a day or 2 to get your playtesting done. And you will receive a guide, another guide like you got on P2 playtesting. You'll need to go through, you'll need to record video footage of you playtesting, giving feedback on these different games, and in return you will receive over 4 hours probably of footage of people playing your game, okay? And that includes your instructors playing your game and giving feedback as well. Okay, so does anyone have any questions? Otherwise, thank you so much for joining us. It's a fun topic to get into. I appreciate your patience with the efficiency lecture. It took us like 3 lectures to get through it, and it's one of our kind of more vanilla and unpolished lectures. So we'll improve it over the summer. I'm looking forward to it. Do you have any questions? Okay. All right. I'm going to step out for just a moment. I will see you at 2:30, and we'll do all of this again. All right? Take care, and we will see you next time. Bye-bye.